Welcome to the webinar on structures product reliability through drop test simulation using Ansys LS-DYNA. I'm Chetan Patil, working as an application engineer for Ansys FEA. So this webinar will be totally based on the Ansys application itself, that is Ansys LS-DYNA. So you like some of you might have heard about LS pre-post LS-DYNA classic one, but this is the Ansys Workbench LS-DYNA, which is particularly replica of explicit dynamic simulation that can be done through Ansys Workbench now. So basically, we do have several different kind of explicit dynamic tools in Ansys, like LS Prepost is there, explicit dynamic tool is there. So we do also have this Ansys LS-DYNA, that is the Workbench LS-DYNA itself. So there you can perform various different kind of explicit simulations. So in those explicit simulations, like today, this particular session is based on the topic of drop test simulation. So we'll have two different kind of models that we're going to simulate over here today. One is your like a generic mobile is available, like a mobile model is available. So on that specific model itself, we are going to see how a drop test simulation is done manually. And we do also have a like a newly introduced kind of tool, that is drop test wizard. So basically we'll be making use of the drop test wizard as well to simulate how the drop test is done using the Ansys explicit dynamic simulation. Ansys explicit dynamic simulations. Like we are not going to make use of the actual explicit dynamic tool which is present in the Ansys Workbench. Instead, we are going to have this overall session to be covered using the Ansys LS-DYNA software itself. So first of all, what are things that we are going to cover in this webinar? We'll discuss about that particular part. So firstly, we'll see why this like Ansys LS-DYNA is mostly important to us, and why do we have to perform these drop test simulations. So why do we usually do perform the drop test simulations on any kind of geometries that we do have, any kind of models that we have? Why do we consider to simulate those kind of models? What conditions are there? And what is the particular use of simulating those? So that we'll discuss in the initial. Then later on, we'll discuss about the implicit and explicit methods. So you like whenever we are performing any kind of nonlinear simulations, so either it is considered to be explicit dynamic simulation or a like implicit dynamic method. So either you might be solving using implicit or explicit, but there is a difference for solving each and every different kind of application. So we will see how to particularly recognize which model should be solved with the implicit method and which should be solved with the explicit method. What is the difference between using those? What are the different time integration methods those are used over there? So we'll discuss about those things, and how Ansys LS-DYNA is capable of solving this explicit and implicit kind of modules over there using the Ansys LS-DYNA tool. We'll discuss about that part as well. Then the next thing that we are going to discuss over here is as we are mostly like whatever this webinar is there, that is planned on the explicit simulations itself, that is drop test is an explicit part. So we are performing the explicit simulation over here. So explicit does include some different kind of topics over there. So from which we are going to discuss about the time step size. So what is the time step size? What are their criterias? How to decide the time step size, and what is mask scaling? So usually mask scaling is used to save your computational time, increase the stability of the problem. So those things, how they are going to help us with like setting up our model, and even giving us better kind of result without taking much amount of computational time, and without creating any kind of instability in the explicit simulations. Explicit simulations usually like are getting affected due to the particular instability in the models. So how to control those things using these two methods, that is time step size and mask scaling method. We'll discuss those things as well in this session. So we'll have two different kind of like demonstrations over here. One will be a introduction to the drop test wizard, which is available in the Ansys LS-DYNA. So this particular demonstration will be having a model of PCB assembly over there. So we'll try to recognize how this particular drop test wizard will be used, how specifically it can be used, and what are the different kind of uses that can be done with this wizard over there. Then the second demonstration will be a generic mobile phone. So drop test will be performed on a generic mobile phone model itself, and we'll do the overall drop test like settings, the overall setup, the conditions to be provided over there for setting up the model will be done manually. So drop test wizard is an automated method to do the drop test simulations. So we'll also look out into how to perform manually a drop test simulation. And then we'll go further with what different kind of applications are available with Ansys LS-DYNA that can be solved and how those can be implemented in the real life. And then at the end, we'll have a question and answer session. So firstly, let us begin with why is it important. So whenever we do create any kind of equipment or any kind of component, so there are many different type of integrated parts in it. So consider just the mobile that has been showcased over here. So mobile is not just made up of an external geometry which has been showcased over here, but there are many different kind of components. Those are integrated inside it, like whether it might be a battery pack, whether it might be a PCB assembly, whether it might be a glass body. So whatever it might be, there are many different number of equipments those are present over there. So whenever we do have integrated parts with it, so when the particular drop test we are performing on such kind of models, we are able to easily recognize what kind of durability is there, what kind of stresses, deformations might get generated. Like even we can find out what kind of reaction forces might get generated on the model and easily recognize what is the kind of reliability this body does sustains. And then we'll also see like basically why we are using this drop test wizard or either drop test simulation is the major thing over here. We do have different kind of behaviors of the geometries. So some of the bodies might be rigid, some of the bodies might be deformable. How to create contacts between such kind of geometries when the body is rigid and one of the body is flexible, if those are in contact with each other, how those particular contacts are created, those things we'll discuss. And then like whenever we are performing such kind of simulations, either it might be a drop test simulation, either any kind of explicit simulation, there are a large amount of higher non-linearities those are been included over here, whether it might be a material non-linearity because of very high like high amount of impact that might be generated on the model. It might affect the particular properties of the material. It might create the material non-linearity. Due to geometric deformations, there might be geometric non-linearity that might be available. And whatever the kind of model that we do have, if we do have multiple number of parts with us, so there are many chances of multiple parts might come into contact with each other. There might not be a direct contact, but there might be some different various kind of contacts those might be getting created between the geometries, like frictional or either any different kind of non-linear contacts might be there. So due to inclusion of all these kind of non-linearities, the overall model becomes highly non-linear. And solving those highly non-linear kind of geometries, highly non-linear kind of simulations is mostly capable to be done using the Ansys LS-DYNA. So which is a particular like replica of LS-DYNA classic itself. So we are like it is still being in the upgradation phase. So there are many other different kind of simulations those can be still performed using the Ansys LS-DYNA. And the major important thing why we are using the explicit solver over here is these particular problems are very short duration problem. So whenever the impact between the geometry does generates, so the duration of generating the impact or occurring the particular non-linearity is very high. So basically the duration time is very low, but the non-linearity is very high. So due to such kind of like problems, those are available where the particular time that is required to obtain higher amount of non-linearity is very less. So we usually do consider those to be solved with explicit simulations itself. And those explicit simulations are specifically to be solved using the Ansys LS-DYNA is mostly recommended. Not only with LS-DYNA, but even the Autodyne solver is as well available through which you can solve this drop test kind of simulation. Now coming to the implicit and explicit part, how do we recognize which particular problem should be solved with what kind of specific like method, whether it might be an implicit method, whether it might be an explicit method. So how we do recognize those? So first thing that we need to always consider is what kind of non-linearity the body is generating, or either to achieve that kind of non-linearity, what is the particular time magnitude. Time magnitude in the sense the duration of time to achieve such kind of non-linearity. So if we are performing a non-linear simulation either it might be a creep simulation, static or dynamic simulation. If such kind of non-linearities take more amount of time, more amount of time to occur, such kind of event. So those kind of non-linear simulations are supposed to be solved using the implicit method. So there are many chances, there are many particular possibilities to solve the quasi-static, the static dynamic, or the drop impact simulation to be solved with both the methods. Some of the particular some of the models can be solved with implicit method as well and explicit method as well. So it is very much like important to recognize which method suits well, because both of them have different kind of time integration method, which does helps you particularly to save your computational time as well and to achieve more accurate kind of results. So whenever we are solving non-linear kind of problem, so when it comes to short duration kind of simulation, so either we do consider drop or impact simulation, which might occur within very short duration of time. It might be 0.01 second. Don't consider the drop height. Just consider the impact that it makes with the ground. So the time that any body makes impacts with the ground when it is dropped from a certain height, just consider the impact time itself. The impact time will be very short. That might be just 0.01 second, 0.001 second, whatever it might be. That particular simulation is considered to be solved with the explicit methods. Ballistic simulations are there. So ballistics usually do have very higher amount of material non-linearity into them. And these kind of ballistic simulations are supposed to be solved with explicit method, because explicit method does allows even material removal as well, and even short duration kind of like events are also supposed to be solved with the explicit method. Then detonation and blast are there. Then even hypervelocity impact analysis are there. Those can be solved with your explicit method itself. So whenever it comes to short duration kind of simulation with very higher amount of non-linearities, those are supposed to be solved with your explicit method, and only those simulations which are having kind of higher non-linearity, but the duration of generating such kind of non-linear events is very high compared to the like short duration simulations. So those kind of simulations are supposed to be solved with your implicit method. And these both the kind of methods can be solved using LS-DYNA. So either it might be LS-DYNA Classic or either it might be Ansys LS-DYNA. Both of the tools are capable of solving both these kind of methods. Either it might be implicit nonlinear simulation or a explicit nonlinear simulation. So these kind of simulations can be solved with Ansys LS-DYNA. That's what we are going to discuss today. So the first thing, whenever we do solve any kind of dynamic simulation, the major important thing, the stiffness matrix that we do consider over here for the simulation is, this is the equation motion that is usually being solved in the background whenever we do solve a dynamic simulation, where there is a mass matrix, acceleration matrix, damping matrix, particular velocity matrix, stiffness matrix, and your particular displacement matrix. Overall, this particular simulation is considered to be solved with both the different kind of methods, that is implicit time integration method and explicit time integration method. Implicit method usually is based on future predictions. So over here you can see, whenever your particular simulation is getting solved, it tries to predict what might be the future next particular solution of the equation. So that particular integration method is very much stable, where you can particularly make use of smaller number of time steps and larger number of time steps as well. So as you can see, whenever we do have acceleration, velocity in a particular simulation, we do consider those kind of simulation to be a transient simulation. And whenever we do have a K, that is stiffness, that is dependent on your particular displacement, we do consider those kind of simulation to be a non-linear simulation. And in explicit simulation, these both the things are available. These both the things does affect the simulation truly. So basically, whenever we are solving a transient simulation, so transient simulation creates more amount of stability issues in a particular problem. And that's why these particular simulations, when we are trying to solve with the explicit method, we need to make use of very smaller number of time steps over here, because this particular explicit time integration method makes use of the current time step itself to particularly solve each and every equations in the simulation. So over here, we need to make use of very smaller number of time steps, so that the sound wave that is traveling through each and every element. So we'll let you I'll let you know what is the element particular sound wave. I'm talking about the particular delta t that is mentioned over here, how that is particularly calculated, how it can be fixed. So we can solve the explicit simulation using the explicit time integration method. So usually in implicit, the future is considered in the particular current simulation to be solved, current equation to be solved. But in the explicit time integration method, the current or the present condition itself is considered over there, and that's why it creates more stability problems. So whenever we do have stability problems, we try to fix them using smaller number of delta t values, that is smaller number of time steps. Whenever we do solve the an implicit time integration method, whatever problem we are solving with implicit time integration method, it makes use of the Newton-Raphson method. So Newton-Raphson method usually tries to predict using the future results over here, and there are lot many like usually you need to solve the simulation where there are convergence issues that might get generated, but these are unconditionally stable. That means you can make use of larger number of time steps and the particular simulation will be still stable over there, but it is not the same for the explicit time integration method. These are somewhat like totally different kind of time integration method from each other. So we are not going to discuss about the implicit time integration method as of now in this particular part, but we are going to discuss about the time integration method of for the explicit one. So how do we consider this delta t to be very much small so that we won't face any issue related to instability in the particular simulation that we are trying to solve? So for that, we do have a particular criteria to solve the simulation with, to calculate the time step with, that is called as a coherent Frederick-Levy criteria. So that is a CFL criteria which we particularly make use of to calculate the time step. So whenever you're using larger kind of time steps, those are usually considered to be solved for those are considered to be used in implicit kind of simulations. But whenever you are using the same kind of larger time steps in explicit simulation, these kind of results might get generated in your particular model. There might be instabilities in the solution that you are trying to solve due to larger size of your particular time step. But when it comes to time step that is calculated specifically with the CFL criteria, at that time you do have proper results, those where you won't face any particular issue related to instabilities and all. So how to generate such kind of results and how to get the CFL criteria satisfied, or whatever the kind of like time step that we are trying to calculate, how to be more precise with it and how to get an accurate value of time steps so that we won't face instability issue in the particular problem. So I hope so this clear might not be like properly visible to all. This is just an image that I have downloaded through like browser itself, so that's why it is not that much clear. So I'll just explain what kind of things those have been mentioned over here. So this is a coherent Frederick Levy stability criteria to maintain the stability in the overall simulation, to control the computational time, and to have a precise and accurate kind of result in the post processing. We do use this particular method to calculate the like time step for the simulation. This time step is not the end time that we are trying to calculate, but this is the only time step for which each and every equation of your simulation is getting solved. So that the overall comprehensive kind of result can be generated at the end of the solution. So over here, we do have the particular CFL criteria available, where delta t is calculated using the formula that is 0.9 into L by C, where L is your characteristic length of the element and C is your speed of sound wave. Speed of sound wave itself you can consider, or either you can consider a stress wave. So basically this is the speed of sound wave or a stress wave through each and every single element that needs to be calculated. So if you define a delta t larger than whatever the like whatever this particular criteria does satisfies, if you define a larger value, that means this sound wave doesn't travel through that smaller kind of elements. So that's why whatever the characteristic length that is mentioned over here, it should be the smallest element in the overall geometry, whatever mesh that you do create. So this particular L value should be the least present value in the overall model, and based on that you should calculate your delta t, so that any particular sound wave or either stress wave won't overlap or either won't pass on any of the element in the overall geometry, and it tries to transfer through each and every element, so that each and every element will be considered in solving that particular equation. So over here, this particular sound wave speed of sound depends on the type of element that you are using. So if you are using a solid element, the particular formula for solid element does changes over here. We do make use of Young's modulus, Poisson's ratio, and density. So sound wave is totally dependent on the material properties itself. So it does totally controls the material property, or you can say the material property does totally control the speed of sound to be traveled from each and every element. Then when you have shell elements in your simulation, you can make use of this particular formula over here. And for beam element, we do have a simple formula, that is C is equals to under root Young's modulus upon density. So these are three different kind of element types, and for each and every different kind of element type, we do have different kind of formula to calculate the speed of wave. Once you calculate those particular values, you can like substitute that in this equation over here, and you do have a characteristic length that can be easily calculated through the software itself. So there itself we will find out the minimum characteristic length in the overall geometry, and through that you can calculate what is this time step that has been calculated through CFL criteria. So once you get that particular value over here for the overall model, you can decide like you will get a precise idea where this particular CFL method is very least, criteria is satisfied with least value, a larger value in the overall model, and which does particularly affects the overall simulations accuracy. I'll let you know how to find out the CFL for any kind of simulation that we are trying to solve. Then once this particular equation is solved, you will have an idea about what amount of computational time is required and what will be the accuracy of the simulation. So why do we make use of the mass scaling over here is to control the time step. So if we have smaller amount of delta t, so as we are considering to have a smaller value, but we should not have very smaller values as well. It should be within some kind of limits over there, so that we won't face much amount of issue with the computational time as well. So to have a better kind of computational time, and even it won't affect with the accuracy, we do have a method that is called as mass scaling. Because in your particular geometry, whatever mesh that you do create, there are very least amount of element sizes that you do generate on the model, and that does affects this L, that is your characteristic length. If characteristic length is very small, then it will obviously affect the delta t. But if your speed of sound is small, that is a smaller value, that will particularly help you with having a larger delta t value for the same kind of mesh. So your delta t is dependent on two different parts, that is mesh that you are creating on the geometry and the material properties that you are using over there. So over here, you are trying to like mass scaling is basically used to increase the particular time step that you are using for the simulation, that is delta t. So how you can increase that is by increasing C. Basically delta t is dependent on L and your C value. So if C is dependent on the material properties, that is density is also included over there. So if you increase the density of your particular material, like not increasing the actual material property, but wherever it is required on each and every element. So we do have different kind of element sizes on the overall model. So as you can see in this particular geometry of R, so we do have several different kind of element sizes present on the model. When we do have such kind of elements present over there, some of the elements will have less amount of mass in it, some of the element have more amount of mass. So density does controls the mass of the particular element. So when we have a larger amount of mass, that means we might have larger amount of density for that element. And if we have larger amount of density over there, we will have smaller amount of sound wave traveling through that element. So if we have smaller amount of sound wave speed traveling over there, that will particularly help us with increasing the delta t in our model. So that's why density is calculated for each and every element, and wherever it is required to increase the mass on the element, that particular region itself will get automatically increased with respect to its mass, so that we can have a better kind of delta t time step defined for the model. So how is this mass scaling is done, and how does it does helps us with particularly saving the computational time and all, we'll discuss it in the demonstration part. So as you can see, both the things are dependent on each other. So CFL and mass scaling, these two things are very much important. So whenever you are done with the calculation of time step, that is for CFL method. So over here you will get some kind of values like this. So whatever the minimum value that is present over here, that will help you. That will particularly affect your simulation with larger kind of computational time and less accuracy as well in the simulation. So this like whatever the minimum regions, those are present in the CFL time step graph, or whatever the kind of result that is generated over here. On that blue colored regions itself, the mass scaling is done. That means the elements those are present in this blue colored region, their particular density or either mass is increased through the mass scaling method over here. So that's why you see this red color region, wherever those blue colored regions are available, there itself the mass or the density of the particular element has been increased, and that particular value itself has been showcased over here. But always mass scaling is not recommended, because mass scaling does not only increases the elemental mass, but the overall geometric mass itself gets affected over here. So that's why uh, just try to add the mass or do the mass scaling to a certain limit, for which you are particularly able to neglect that kind of mass if it is added to the geometry. Then the next thing that we are going to discuss is about the drop test wizard. What is this drop test wizard, and how we are going to apply it on our geometry, whatever we are going to use over there. So this is a fully automated method. We just have to define the drop conditions over here. Like if our model is dropping at a certain height and at a certain angle, we just have to define those things over here. And overall fully automated method will be applied on your geometry to just perform your simulation by clicking on the solve option. This particular method does requires only the geometry. Nothing else is required over here. What it does is it creates rigid construction geometry. That means whatever geometry that will be dropping on. So it will create a ground layer over there, which will be your rigid construction geometry. Then it allows orientation of the object and the drop plane. So orientation in the sense, basically if it is like dropping at a certain angle or a certain kind of distance, those things can be applied over there. It calculates and applies impact velocity based on the drop height. So whatever drop height you will mention over there, it will convert that particular drop height into a impact velocity, and that will be applied on your geometry. So you don't have to, like usually whenever we used to do the drop test simulations previously, like we used to consider the like the rigid plane at the bottom, and from wherever we are dropping the object, we used to place the object over there at the certain height. But explicit simulation solves the overall model from the initial position of the geometry till it impacts with the ground. But that does takes very high amount of computational time. This simulation will help you with saving out those amount of time. Instead of placing your model at a certain drop height, instead it will take your model closer to the ground, and then it will apply the impact velocity that is generated in your model through certain amount of drop height. So that impact velocity will be calculated automatically, and that will be applied on your geometry, so that even your model, if it is closer to the ground, it will have the same amount of impact velocity or the internal energy present inside it, that will get generated on the model, and due to which we can have the actual kind of impact simulation over there. Then like it applies standard earth gravity as well automatically. So fully constrained drop plane will be applied. So whatever the rigid or the ground geometry will be created, that will be fully constrained over there. So you don't have to worry about it, even over constrained or under constrained kind of conditions. defines body interaction between the drop plane on the objects, and even meshes the model. So basically, whatever the kind of requirement of the mesh is there for this kind of simulation, it totally does the meshing as well based on the conditions that you have provided or whatever those are required for this simulation. So it will automatically either calculate it or either it will use the conditions that you have provided on your own. Then sets analysis end time as well. So it will automatically calculates on its own what kind of end time is required for the simulation to take place. And like there is an appendix that I'll showcase you how like these kind of models can be downloaded and you can particularly solve the simulation. So first simulation that we are going to solve is on a PCB model. So we are going to make use of the drop test wizard over here. So this drop test wizard, the goal of solving this particular simulation is to just make use of the drop test wizard to simplify the setup of drop test simulation of this circuit board. And then the procedure that we are going to use over here is defining the mesh size over here. So either you can define your own conditions for the meshing, or it will take on its own and it will just give you the model with the whatever required mesh size is there. And either you can just go with whatever automated process is there. So use the procedure that we are going to use is to make use of the drop test wizard to apply the drop test conditions and solve and review the results that we are interested in. Then the second demonstration that we are going to have over here is on the drop test of the generic mobile phone. So we do have such kind of model available with us, and on such kind of geometry itself, we are going to run the simulation, and we are trying to find out like with manual conditions. We are not going to make use of any drop test wizard. The drop test wizard can be applied for this model as well, but we are not going to make use of that drop test wizard, but we'll see how this particular simulation can be solved without applying a drop test wizard over here. So the overall workflow that we are going to use for solving this drop test is, first of all, we do have the geometry already created with us, and I do also have the material properties. Those are supposed to be assigned to the geometry. So those things are initially done for my model. So I do already have those kind of models available with me. So even if though you guys want to practice the same kind of models with, then I'll share the link for downloading these models as well, or either I'll share you the workbench file itself so you can just go through that. And if you want to practice it, you can just go through the models as well and the contents that I have shared, that I'll share, sorry. Then we'll also go with the connections between the geometries that we are going to use, how to make the contacts and the body interactions for explicit simulations. Then the mesh that we are going to generate, the initial conditions we are going to provide, the constraints we are going to apply, the kind of analysis setting, that is the time step and the particular end time that we are going to decide and solve it. And then we'll do the model check, then model corrections if required, and we'll rerun the model with any kind of variations with the conditions that we have provided, and we'll try to do the post-processing part. Then the condition that I have provided for the drop test to this mobile phone is calculated through this formula. We'll discuss this while going for the next demonstration. But first of all, we'll go with the first demonstration of our simulation over here. So firstly, I'll just go with the drop test wizard. Just give me a second. I'll share my screen. Okay, so I hope this screen might be visible to all. So over here, already the model was created. So there is nothing else that I have done over here. Just I have included the material properties. So it might take more amount of time. So I have already imported the materials over here with respective properties to be defined to them. So over here we do have the aluminum material for aluminum 6061. So over here we do have defined the properties, that is linear elasticity and bilinear isotropic hardening plasticity properties to this material, which will be applied to the heat sink of the circuit board. And then PCB is PCB material I have created over here. So it does have the linear elasticity, the bilinear isotropic plastic properties as well. And even there is an extra property that I have included over here, that is plastic strain failure. So this property can be included if you are interested in finding out the material failure in the simulation, because you are solving the explicit simulation, so you can easily find out the material failure in the models as well. But for that, you need to turn on some of the output controls as well to visualize the result for the plastic strain failures in the model. But we are going to make use of these two materials for the simulation. The geometry has been imported already over here, so I won't be going into the geometry. I'll directly jump onto the Ansys mechanical itself to load the model over there to showcase you what kind of model it is and what kind of geometries are available, and for what kind of geometry I have defined which specific materials. We'll discuss about that, and then we'll jump on to the drop test wizard. Okay, so the model has been imported over here. So we do have this particular geometry where we do have the heat sink available. We do have some memory chips over here. We do have a CPU as well, which is available at the bottom of the heat sink, and we do have the PCB available over here. So these are some of the geometric components which are available: the heat sink, the memories, the CPU, and the PCB board. So this PCB board is a surface geometry which is available. Always try to have a better kind of geometric settings whenever you are trying to solve such kind of models. So over here, what we are going to do is, first of all, this geometry has been imported properly, and for each of the geometries, there are specific materials those have been defined to them. So for the heat sink, we have already defined the SN material, that is aluminum 6061. And for remaining all the materials, we have defined the particular PCB material properties to them. Then once this is done, we will go to the particular connection sections over here. There are some automatic connections or contacts those have already been created between the geometries, and like there is no difference between creating contacts or either defining body interaction. Body interaction is only done when you are not sure with what kind of connections to be developed between the geometry, like in which specific region the connection should be developed or the context should be developed. If you are not sure with those, we usually make use of the body interactions in the explicit simulations. So over here, whatever contacts those have been created, we'll try to make use of these contacts itself. We are not going to modify anything from the geometry over here. So these contacts have already been created for the geometry, and this body interaction has been developed for the overall model. It does depends what kind of simulation you are trying to solve. Currently, the overall body interaction is not required because all the geometries which are present over here, all of them are the bonded contact itself. So body interaction between these bodies itself is not required, but body interaction is required when we are defining the particular ground body as well over here, the rigid body on which this body will be dropping. So over here, first of all, we don't have that impact geometry as well, because this PCB will be like dropping at a certain height on the ground. So we don't have the ground geometry over here. So either what you can do is you can create a construction geometry over here. So you can create a surface or a solid, and you can define it to be a rigid geometry, and you can create it over here. But overall, all those process will be done automatically by the drop test itself. It will create the particular like construction geometry as well. So at whatever kind of angle you want to rotate your geometry. And the first major important thing is your model will be considered to be dropped in the negative y direction. So always try to place your model with respect to the axis itself. Keep always the x-axis in your normal direction, and YZ to be your particular normal plane itself. So this Y direction, negative Y direction will be the dropping side of the model. I'll let you know how that drop test is done. So first of all, like whatever the contacts those are created, we are not going to modify any of the contacts which are present. We'll try to modify the body interaction, but it is not required as of now because there is no further any geometry that has been included over here. We'll first of all jump on to the meshing, but firstly we'll go with the metric system, that is units. I don't want to go with the Instead, I'll go with the metric system in terms of meters over here, and I'll define the element size for the geometry. So as you can see, the physics preference is already defined to be explicit. So explicit will always make use of the element order, that is linear one. And over here, we'll make use of the element size, that is 0.003 for the overall geometry. And as we do have some kind of curvatures over here, we'll try to turn on the curvature as well, which is already been turned on, and we'll define the same minimum size that we did defined over there for the element sizes. So a constant kind of element size will be created on the overall geometry over here. And once this is done, either I'll just right click and try to generate the mesh. But as of now, we are going to make use of the drop test wizard. So you don't have to like generate the mesh, because once you go for the drop test wizard creation, at that time it will automatically create the overall process. Now we don't even have to define the conditions in the LS-DYNA. You can see the analysis end time is not been defined over here. There are no initial conditions, those have been defined. There is no mesh that has been created on the geometry. Then there are no further any inclusion that has been done, which is required for the drop test simulation. But what we can do over here is, if I click on the LS-DYNA option which is present over here, the solution, the environment which is present, there you will find out in the ribbon bar, we do have a drop test wizard that is available, which is a fully automated process. So if I would click on the drop test over here, your model will be showcased. So over here in the bottom, we do have the help menu that will let you know what kind of things we are defining in the particular input section. So first thing is target rotation. So if you're trying to rotate your model, you can rotate it about x-axis, y-axis, and z-axis. It does depends on you. And you can see over here the drop direction is negative y direction in global axis. So that's why always your model will be dropped in the negative y direction itself. And you can rotate your model in all these three directions, whichever you want. So I'll define the particular rotation for my model to be negative 25, or either like let us just consider 40 degree. So I'll define a drop rotation of 40 degree over here. So as you can see, my model has automatically been transformed from its original alignment to the particular orientation that I did defined over here in the drop rotation. It has automatically applied a part transform over here on the geometry, and which has particularly rotated my model. It has automatically created a rotation point as well over here with respect to the coordinate system itself, which was present from the initial. Then there might be some other settings, those might be done over here, but there are lot many other things, those will get generated after you define the next option. So you have to define the drop height over here. So the current drop height is 1 meter. Let us just consider 1 meter itself for our particular simulation. Either you can go with drop height or impact velocity. But if you don't know what is the actual impact velocity to the ground, you should always go with the drop height, because it is always known to us. So drop height, I'm considering to be 1 meter. So whatever the particular impact velocity is there, it can be easily calculated with the formula that I did mention over there in the PPT. So this specific formula itself will be used to calculate the impact velocity on the model. So these calculations will be automatically done on the model by the drop test wizard. So we don't have to worry about that for this specific model. But when we'll go for the mobile phone model, at that time, we will have to calculate it and apply it on the geometry. So I'll just click on the next option over here. When you'll click on the next option, you can see it has created a ground geometry as well, which is your rigid geometry. So many further settings have been done. You can see a construction geometry has been created, which is this particular specific geometry. And this specific geometry is now a rigid geometry, which has been defined already over here in the stiffness behavior. Then there is a collision point that has been defined over here between both the models. So this point is the collision point where both the models will be impacting with each other. And then we do have this impact like drop height that has been defined over here, where you can find out the impact velocity as well, predefined into it. And the direction of the like drop test has been defined over here. Dropping of your model has been defined in the negative y direction itself, and it will automatically add up a standard earth gravity as well once you are finished with your particular setting of the drop test. Now it is asking us what is the drop test behavior, the frictional behavior of the geometries when it impacts with the ground body. So when this PCB body interacts with this ground body, we want a frictional kind of contact or behavior should be generated between the bodies, where the friction coefficient will be 0.1 for them. Once I'll define this specific value over here, automatically the body interaction will be updated between all these geometries and the ground geometry. But instead of defining the body interaction between all the geometries, we have to keep it specific between these two geometries itself, that is PCB board and the ground body, because these bodies won't leave this specific geometry, because it will be impacting at a certain angle, and these geometries won't come into contact with the ground body, so we don't want interaction with them. So once that is done, I'll just click on the finish option over here, and you can see a standard earth gravity has been applied over there. Now currently the meshing is generating on the model over here. Once the meshing is done, we'll also check the CFL time step that will be calculated for this model, and automatically some of the results will be developed in the solution, that is total deformation and total acceleration for the overall model. But whatever component we are interested in, we'll just try to recognize for that particular component itself. So it might take a little bit of time to generate the mesh on this geometry over here. So the second one, like the second demonstration, I'll just showcase you the actual solved file itself, so that we don't have to face much amount of computational time once again to solve that model and try to show you the results. I'll just showcase you the overall setup that I have done with the second demonstration, and then I'll just showcase you the results that I have got from the model over there. So over here, currently it is generating the meshing. It won't take much amount of time. Just this is the last step that we are doing with the drop test. Once this is done, we are ready to go with the solution. Okay, so as you can see, the mesh has been generated on the overall geometry over here, and the setup has been finished. So you can see the total deformation and total acceleration has also been applied over here. There is a fixed constant that has been applied to the ground geometry, and there is a standard earth gravity that has been applied to this overall geometry itself over here. And in the analysis setting, you can see already automated calculated end time has been generated over here, which is 0.002 seconds. So that calculated value will be specifically suitable for this model. If it doesn't suits, you can modify it, but mostly the calculated value is always the like correct itself for this drop test wizard. So over here, between whatever the body interaction that has been created, that is for all the geometries, but we don't want for it to be for the all geometries, but only between the PCB and the uh, rigid geometry, that is ground geometry. So I'll apply it in between both the geometries over here, and the friction coefficient has automatically defined between both the things. And there is all these settings, those have been done already with the geometry section over here. Now we are just ready with solving our model. Before that, we'll include some of the results, and before directly jumping on to the results that we are interested in to find out through the solution, we'll also try to include the CFL time step over here. So this particular thing, that is CFL time step, will calculate the minimum time step that it will take to solve the simulation based on your mesh that you have generated on the geometry. So I have included the CFL time step. This is the rigid body, and it has been automatically calculated through the generated through the drop test. So this is not the inclusion of our simulation. We are interested in this overall consideration of the PCB model. So I'll just click on apply over here and click on show all geometries. And once that is done, I'll click on generate for the CFL time step. So you can see what kind of time steps those have been calculated over here. So the minimum that is available is 1.2979 e raised to minus 7 is the minimum time step that has been calculated for this model. So based on this, whatever the kind of end time that has been calculated over here, this end time and whatever the number of cycles are there, if you divide end time with maximum number of cycle, if it is not less than the CFL minimum time step, then your simulation will have the energy problems. So it will define the energy is too large and your simulation will get stopped at that initial itself. But always your end time should be less than whatever the minimum value that has been calculated. But this value can also be increased with respect to mass scaling, or either you can even modify the mesh that you have generated on the geometry to increase these values over here. This way you can find out the CFL time step. Once this is calculated, you can even find out the characteristic length of the elements as well over here. So you can see the minimum characteristic length is 0.0009 meters. So that might be 0.9 meters itself for the geometry. Sorry, for the geometry. So based on it, if you try to calculate for, the particular results for your model, you will have a better idea what what would be the CFL time step minimum and maximum values. And maximum doesn't need any kind of modifications, only the minimum one requires the modifications over here. Once that is done, you can do the mass scaling in the analysis setting, but for this model, it is not required as of now. So there is an option called as automated mass scaling over here, which can be turned on. But for the next simulation, I'll showcase you what happens when we turn it on. Next, we are going to just solve the simulation, but before solving it, I'll just try to include some of the results. So before including that particular result as well, you can do one thing. You can insert some of the results related to your, not these ones. So we'll go to the LS-DYNA pre. Over here, we do have some kind of trackers which showcases the body contact tracker. If you are interested in finding out the contact force on the geometries, then we have the body contact tracker over here. So we can define these two geometries over here inside this body contact tracker. And then if I would go to the solution information, or either only this particular geometry on which this body might be impacting, and there will be a particular contact force that might be getting created. And to visualize that contact force, you can go to the solution information and import the contact force over here. Instead of geometry selection is correct, we want the body interaction to be considered over here between these two geometries. And for this particular region itself, we have created the body contact tracker. And for this one itself, we want the force contact force to be calculated. Now the contact force will be generated with respect to y-axis because the impact is in y direction. So we'll have the y-axis over here. Then similarly, we'll try to calculate the particular kinetic energy generated in the model due to whatever the kind of geometry that we do have. So not this particular model to be available for calculating the kinetic energy. The remaining bodies which we did imported over here, that will be considered to calculate the kinetic energy. Similarly, how kinetic energy is converted into your internal energy, that can be also found out. Will internal energy as well over here. Then we are interested in finding out the acceleration on the CPU itself. So the major concerned region in our geometry is the CPU region over here. So we are interested in finding out the stresses and deformations on this CPU body itself. So we can insert stress results as well over here. So there is no strain result that is available as of now for this particular simulation, because in the analysis setting in the output controls, you have the option to turn on the strain results as well over here. But currently it has set to no. So it will save your computational time. But if you are interested in finding out the strain results as well, and based on the strain output, if you are interested in removing the materials from the geometry, then you can go for the particular strain results as well. It will take more amount of just your computational time. So once it is done, I'll just click on the solve option over here. So the overall simulation will get started to be solved. So first of all, we'll go to the solution information. Over here, you can see how much amount of time it might take to solve the simulation. That is somewhat around 9 minutes of simulation time has been estimated over here. So it will take morely 9 minutes of time to solve this overall model. Meanwhile, we'll go for the second demonstration that we are about to complete over here. So I'll just open the solved one itself. So already I do have the solved one as well available with me. So you can see that cycles are being performed in the background. This will create a key input file as well, which we usually create for the Ansys LS-DYNA. That particular file can be even accessed over here, but I guess though it might be okay. So the solver directory is available over here. So we do also have the key input file over here, which we usually do create for Ansys LS-DYNA, the classic one. But you can see with respect to the graphics one as well, we are creating the same kind of input file over here. This input file, if you are interested in trying to solve the same kind of simulation using the Ansys LS-DYNA classic one, you can just import this key input file over there in the Ansys LS-DYNA classic one and try to solve the simulation and compare the results that you are getting from the simulation. So once this is done, okay, so it's still solving over here. We'll meanwhile go for the solved one. So I guess this is the solved one which is available over here. So I'll just try to open the model itself over here directly. The engineering data, the material properties and geometry have already been defined for the overall model. So that's not the thing that I'm interested in showcasing, but the setup that I have made with the model, that I just want to showcase you how manual settings are being done for this drop test simulation for any kind of other geometries. So over here, this is the model that I have used for the simulation. So if I would just click on show all geometries, so we do have such kind of geometry with us, where we do have the housing of the mobile, which we also call as the casing of the mobile phone. So we do have this casing at the outer, we do have the ground to impact. So all these geometries are manually created. None of the geometry is created automatically using the drop test wizard. There is no such use of drop test wizard in the overall simulation over here. This is the glass body. If I would hide this particular geometry, you can find out the PCB inside, mounted inside this overall geometry mobile phone. There are some screws to mount that PCB inside the mobile phone. There is a geometry, there is a pole surface which is available over here. So all these geometric components are available in the overall model. Those are being used over here for the simulation. The materials has been defined to each and every component of the geometry. And you can see I have created some of the contacts between each and every geometry manually over here. So there are some automated contacts, those will be getting created, but whatever specific requirement is there for your simulation, you can just create those. And as of now, like there are some contacts that I'm still missing with, or either whatever the mesh that I have created, it is not totally like finer near about wherever the impact is getting generated. So there might be some issue with the results. That is, some penetration issues are there, but those can be resolved once I will just have some better kind of quality of mesh on the geometry. So over here, the body interaction has been defined between the geometries which will come into contact with each other. So these bodies itself have defined with the like body interaction. That is, the frictional body interaction has been defined with the friction coefficient of 0.15, and each and every contacts have been created. Either some of them are the bonded one and some of them are the frictional. Those are your non-linear kind of contacts. And there are many materials those have been defined for the overall model. There is even glass material as well, which is present over here. There are elastomers, plastics, acrylic glass, which is present over here. So these are totally highly non-linear kind of materials. Those have been defined for each and every geometry. So such kind of simulations can be solved using the Ansys LS-DYNA. We have even defined this rigid body additional nodes connection between the bodies, that is rigid bodies and your flexible bodies over here. So this option will be available in the Ansys LS-DYNA pre. So if you would go to the pre section of the model, there you will find out some rigid body tools where you can provide rigid body rotation, forces, movement, constraints. Then there is rigid body additional nodes. So you can create some rigid body additional nodes between the geometries to make better connection between rigid bodies and flexible bodies over here. Then I have also calculated the CFL time method time step over here for this geometry that I have meshed, because this body I have considered totally to be constrained over here. This is the rigid part of the geometry where we want the this is the ground part, so where the particular impact will take place. And then if I would go to the analysis settings over here, I have defined the end time to be 0.003 seconds, and nothing I have changed over here. Just I have turned on the automatic mask scaling. So based on your CFL time, to have a better kind of like time step to be defined for with respect to the mesh that I have created, I have turned on the automatic mask scaling as well, which will control the overall time step of the simulation. So over here, I have even defined the earth gravity as well in the negative y direction itself, and I have applied a body constraint to this like geometry. The rigid body constraint has been applied over here, which is available in the rigid body tool, through which you can apply some rigid body constraint. So these options are only available for the explicit or LS-DYNA simulations itself to be performed using the Ansys LS-DYNA. Now, in the initial condition, I have applied an impact velocity over here. So this impact velocity has been defined in the component way. In the negative y direction, I have defined this particular component impact velocity. So that is of value minus 5425, which was calculated through the formula that I did showcased over here, through which I did applied this particular thing on the mobile geometry. So this height, if you are known with, then you can calculate the impact velocity of the model, and through which I did calculated it, and I have applied the same kind of value on the geometry. This simulation was to showcase what kind of mass scaling gets added to the geometries, but I have just calculated the mass added masses on the geometry in specific regions itself. So if I would go to the added mass, once the simulation is solved, you can see the simulation results over here. The deformation in the geometry is just 0.7 mm on the model. So if you would just check the kind of penetration that is being generated, this is because of the kind of element quality and the contact that I have generated that can be resolved later on. But the actual deformation in the geometry is getting generated in these particular regions over here. So more amount of deformation is getting generated over here. If I would go to the added mass, so you can see over here, the added mass that has been calculated only for what kind of geometry, that is this pole which is connecting your particular battery pack with the housing of the model. So this particular pole which is available over here has the higher amount of added mass that has been done over here. You can see what amount of mass is being added to this geometry to increase the time step over here. With respect to each and every time step, what amount of mass is being added to the particular elements, those has been recorded over here. And this is the data that has been calculated. Then if I would go to the another added mass component that I have calculated this for, that is your housing the lower housing of the geometry or the casing of the mobile phone. So over there as well, there is more amount of added mass that has been calculated over here. So this is based on your particular CFL time step that has been generated over there on the model. So if you would check the CFL time step, the minimum value is present over here on the pole region itself. And there itself, your more amount of mass has been added over there. So you can calculate that particular thing through this method as well. Now coming to the kinetic results as well over here. So you can see what kind of results have been generated on the model. So this is the contact energy that has been generated over here because of the impact that has been developed. Then there is some amount of kinetic energy that has been converted to your internal energy and contact energy. And if you would go to the total deformation, these are the results that you are getting through the manual settings. So let's just check whether the simulation has solved for this PCB as well. Okay, so it's still solving over here. So if I would just right click and click on insert deformation plot tracker. So with respect to the current time step that is being running on, we'll check what kind of deformation that has been generated on the model over here. So if I would just right click and show all bodies, so we can have this impact of all the bodies to be showcased on our screen. So if I would go to the results to have scope body instead of scope body, all body, smooth contours with just wireframe. So you can see the actual deformation in the body from its original position, what kind of deformation and impact that has been generated over here up till now. So this way you can perform the simulations over here. So it is still solving the overall model. If I would just go to the energy summary over here, you can see how the kinetic energy is getting converted to an internal energy in the model. So that is because your particular kinetic energy is getting converted to internal energy because of the drop or the impact that is being created between the geometries. And there is this some amount of contact energy as well that is being generated between the models. So let us just wait for the model to get solved. Even I guess to the contact forces and all other things will be showcased as, yeah. So as you can see the contact force over here, this is the time when the impact has been generated between the bodies. And then later on, what kind of contact force has been increased in the overall model in the y direction that has been calculated over here, just on the ground part itself. And then if you would go to the kinetic energy, this kinetic energy value, you can calculate it through the formula that is half mv square. So m is your particular mass of the geometry, but the mass that we are considering over here is of 71 bodies, that is this particular PCB model itself. So if you would just consider the mass of that particular part and multiply with the impact velocity square, then you will automatically get what kind of kinetic energy would be present in the model in terms of joules. So this value will be generated over there. And once this value is generated after the impact, how this kinetic energy is getting converted to an internal energy, you can find it out over here. So I guess the simulation has been solved. Now, if I would run the simulation or run the animation over here, you can easily find out what kind of deformation after impact or drop is getting generated on the model over here. And then if I would just go to the acceleration that we did try to find out for this particular CPU, which is present over here, then if I would play the animation, you can see what kind of acceleration that has been generated. The value is being calculated over here for this CPU model itself. And the stress that is being generated on the CPU in terms of megapascals, if we are trying to analyze the results, then we can have those results as well. That is 7 megapascals of stress has been generated in the sharp corner region. So that can be even evaluated in a better way with some kind of curvatures on the model. So this way you can solve the overall drop test simulations for any kind of geometries that you do have, either through the automated process of drop test wizard or either through the process of manual definition of the setup for drop test simulations.